Let's see how to incorporate this rotational kinetic energy into our conservation of energy idea. Our example, the pulley is a solid disk of mass big M and radius r with rotational inertia 1/2 mr squared. 2 blocks hang from the sides of the pulley by a light cord. Initially, the system is at rest, with block 1 on the floor and block 2 held at height h. Block 2 is then released and allowed to fall. And we are, for part A, trying to find what is the speed of block 2 just before it strikes the ground. We're going to write our answer in terms of m1, m2, the mass of the disk itself, r, h, and g. All right, so we're using, again, the ideas of conservation of energy. The difference here versus what we've dealt with before is that our pulley now has a mass, which means it contributes to the system. And so remember how I said if we were dealing with solid objects, we would be given that rotational inertia equation. And so in this case, for our disk, it'll be 1/2 mr squared. The other thing to take note, they do tell us the cord, it's a light cord, so probably negligible mass, so we don't have to incorporate that into our system. All right, let's take a look at conservation of energy. Of course, we know the energy at one point in time, our initial energy, is equal to our energy at some later point in time, what we could call the final energy. And our initial energy is as we're holding block 2 up before or just as we release the system. And so initially the system is at rest and block 2 is held at a height h. So at that moment, the only energy is our gravitational potential energy. So UG. All right. At the point in time just before it strikes the ground, we know that when we release this, block 2 is going to fall down that full distance h, and block 1 is going to be raised that distance h because they are connected. This is a solid string, so they're changing height together. They're moving together through that. Other things we know, at that moment, both M1 and M2 will still be moving because it is just before it strikes the ground. So they will be moving translationally, just straight up or straight down. But then that means our pulley itself will also be moving. So it will be rotating. So here, I guess I could be more specific. Over here, our initial energy, this is the initial energy, potential energy for block 2. Just as the system is hitting the ground, we're going to have our rotational kinetic energy from the pulley. We're going to have the kinetic energy of block 1, the kinetic energy of block 2, and at that point in time, the gravitational potential energy for block 1. And so this is what our setup looks like here. And now we just want to go through and put in some more specifics. I'm going to keep it general. I'm not going to put in, I'll put in some details like M1 and M2 just to keep it clear which term we're looking at. So our initial gravitational potential is M2GH. Our rotational kinetic energy, 1/2 I omega squared. The kinetic energy for block 1, 1/2 M1 V squared plus 1/2 M2 V squared plus M1 GH. So things we know, these H's again are the same H's, so we don't have to label them separately. We also know that the velocities are the same because, again, the system is moving together. So it's experienced the same acceleration for the same distance. The last thing we want to do is be a little more specific about what's going on over here with this rotational kinetic energy. We want to go ahead and put in our expression for I, 1/2 capital M R squared. The other thing we want to do is let's put omega in terms of V. That way, again, the system's moving together. We're showing that they all have that same tangential velocity going. So I'm going to only change that rotational kinetic energy in this step. So M2, well, I'm going to do one other thing, GH. I'm going to move over our gravitational potential from the other side as well. So I'm going to subtract M1 GH, and then I'm going to change our rotational kinetic energy, I, is 1/2 big M, big R squared. And let's go ahead and change omega as well. Omega is the same as V over R squared. And then plus 1/2 M1 V squared plus M2 V squared. All right, from here, it's just keeping track of some algebra. I'm going to kind of factor things down just to make it look a little more condensed. So over here on the right, that's the left. We have GH in both of these terms. So I'm going to factor that out. We're going to be left with M2 minus M1 GH equals. And then let's condense this down a little bit more. First of all of these terms have 1/2 in them. And now that we've kind of looked at it, they all have V squared in them. So I'm going to go ahead and factor out 1/2 V squared. That's going to leave 1/2 big M. Our R squareds will fully cancel each other out. And then we'll have plus M1 plus M2. And so we can condense this down quite a bit. Let's see what we can do next. We are trying to solve this for V. So we could go ahead, multiply both sides by 2, divide both sides by that 1/2 big M plus M1 plus M2. So that's going to give us V squared is 2 M2 minus M1 GH over 1/2 big M plus M1 plus M2. All right, we are almost there. Last bit to get the speed. Right now we have V squared. We're just going to take the square root of this. So the speed of block 2, it's also the speed of block 1. It's also the tangential speed of the pulley. Because like we've been saying, they're all related. They're all moving together. V is the square root of 2 M2 minus M1 GH over 1/2 big M plus M1 plus M2. And that is our solution.